All right, let's get started. And today we're going to discuss about a relatively recent class of database systems, which are often called NewSQL systems. Now, this material that we will discuss today, it's not covered in our course book anymore, but if you're interested in those topics and want to get more information, then please have a look at those papers that you see listed here. All right. So the last time we have seen the CAP theorem, which essentially says that there is a tension between consistency and availability. And consistency in this context means essentially that different copies of the data in a distributed system stored on different sites are in sync, so to speak. Availability means that the system is able to serve requests. And we have seen a little example showing that if you have a complete network partition, meaning that you have different components of your system that cannot talk to each other because the network is down, for instance. In that case, you might have to decide between consistency and availability, because if somebody sends a request to one part of the system, then that part of the system either refuses to honor the request or it updates its data locally, and then the local data might become inconsistent with data at a different site. So the CAP theorem basically says there is kind of a tension between those two, and perhaps we have to choose which one is more important to us. And traditional database management systems, they prioritize a consistent data above everything else. So in the example, they would refuse the incoming request rather than make the data inconsistent. There's a class of systems called NoSQL systems, which typically favor availability over consistency. So if they have a choice, they would rather say, okay, we accept that data becomes a little bit inconsistent, but in exchange, we are able to answer the request. And that can be particularly important for scenarios like online shopping, for instance, because here, if you refuse requests, it means we lose sales and therefore money. So the last time we have seen a couple of systems that fall into this category of so-called NoSQL systems. Now, the CAP theorem has been criticized. The points that you see here are actually by the original author of the CAP theorem. He wrote another paper later in which he critically discusses the CAP theorem. Among the points mentioned are, for instance, that the CAP theorem focuses on relatively extreme cases. If you really have a system where different parts cannot at all talk to each other anymore, that might be rare. And also, we consider consistency and availability as something binary in the CAP theorem, and that, of course, is a simplification. In practice, you have a lot more choices. For instance, you don't have to decide in general which of the two, availability or consistency, is more important. You could decide that for each single transaction or for each single user. So this is more flexible than what it sounds like in the CAP theorem. And also consistency, it's not really a binary property, but it's there's a whole range of different consistency levels, so to speak. So altogether, the point is that the CAP theorem simplifies a couple of things, and that the choices might not be as strict as it suggests. Now, this has led to a new wave of systems that are often called a NewSQL. And the NewSQL essentially means that we try to get back consistency guarantees, we try to get back asset guarantees when processing transactions, while at the same time maintaining high performance by exploiting a couple of new ideas and new developments, for instance, when it comes to the hardware. Now, this is a little overview of the different categories of systems that we have been discussing in the past few lectures. Of course, there's the so-called traditional distributed database management systems, which aim to guarantee ACID transactions, even if it comes at the expense of performance. Then we have seen a NoSQL systems, which is a broad term, but often it entails that we are giving up ACID guarantees for higher performance. That was the case, for instance, for those systems that we have seen last time. Now, in this lecture, we're going to focus on a few more recent systems dubbed NewSQL, which try to get the guarantees of ACID transaction processing, while at the same time having high performance and availability. We're going to discuss two systems in that category. The first one is HStore, which was also commercialized under the name VoltsDB. And the other one is a product by Google, which is called Google Spanner. We start by discussing about HStore. Now, HStore, the design of HStore is based on a couple of observations about modern transaction workloads and modern hardware. For instance, it used to be not uncommon that we had a relatively long-running transactions. In modern workload, those transactions are typically extremely short. And also those transactions, they execute automatically. So unlike prior transactions, they don't require any input from the user at any point, which will significantly slow down transaction processing. Furthermore, the transactions typically correspond to templates that are known in advance. I mean, one typical application scenario is, for instance, a database system that is accessed not by writing SQL queries and transactions, but rather over a web interface. If you as a customer do online shopping, for instance, then the web interface often triggers transactions in a database in the background, but the templates of those transactions are already known before runtime because they have to be in sync with the web interface. So they only depend on the specific parameters that you enter in some of the fields in the web interface, but the structure of the transaction is already decided a priori. There's also a couple of changes on the hardware side. It used to be prohibitively expensive to put databases into main memory because main memory used to be very expensive. Nowadays, main memory has become cheap enough that for most databases in practice, it is actually feasible to fit them entirely into main memory. And then, of course, on the other side, what has changed is that nowadays, typically, if we build a system, then in most cases, it's going to be a distributed system. And altogether, those observations entail a couple of design decisions for the HStore database system. So if you look at those observations, is there perhaps anything that comes to mind for you about the design implications for database systems? So if you look at those properties of modern hardware and modern workloads, does it suggest changing the design of database systems in any way? The authors of HStore certainly thought this way, and we will see in the following how HStore exploits those properties here. But I already wanted to ask whether anything spontaneously comes to mind about how those observations influence the database design. Okay, that's a good point. Recovery might be more difficult. Okay, why might it be more difficult? All right, okay. So very good, yes. So here, if we can fit the database into main memory, then we probably want to do that because it is faster. But if we do that, then recovery becomes much more difficult. Now, if you think, for instance, about concurrency control, we initially said that we want to interleave the operations of different transactions for multiple reasons. Can anyone remember what the reasons were that we want to interleave the steps of different transactions? Yes, very good. There's a first reason, because long-running transactions would delay shorter transactions that are blocked behind them. If one user in the system is running this big transaction that takes an hour to finish, and if we don't interleave steps from different transactions, then all the other users with very short running transactions would be blocked behind that 1 hour transaction. And that would make everyone unhappy, basically. So yes, if there's long running transactions, then we want to interleave operations from multiple transactions. Long running transactions, yes. Specifically, we discussed about a situation in which transactions often remain idle because they have to wait. And in those situations, it makes sense to squeeze in a step from a different transaction. So what is it that transaction often need to wait for? Very good. Here the suggestion is that we have to wait in order to read data from hard disk. Very good. So that is the other big motivation for interleaving the steps of different transactions, because if one transaction is waiting to get data from hard disk, then another transaction whose data is already in main memory may as well proceed. Very good. Now looking at those changes here, what do you conclude for concurrency control? So okay, very good, yes, exactly. So I mean, initially we said we don't want to execute transactions serially because of long-running transactions, because of waiting for data from hard disk. But now we are in main memory, so we don't wait for data from hard disk anymore. And all of our transactions tend to be short running. So for those reasons, there's actually no real motivation anymore not to run transactions serially, because it simplifies a lot of things. We have seen that concurrency control can be complex and it can cause overheads. But if I can just execute transactions serially, then it is probably the simplest thing to do. Okay, very good. There's also the point about transactions corresponding to templates. Is there any way in which I can exploit having some knowledge about the transactions before runtime? If somebody told you which transactions, roughly, which transactions are executed at runtime, what could you do in preparation in order to make data processing faster? Okay, we could load data in advance. And I mean, here we assume that everything is, everything is generally in main memory, and we would load the data before runtime into main memory. Yes, that is correct. What other decisions could you make if you know in advance approximately which transactions will come in? You have a lot of data. It is distributed over different nodes in your network. Is there some decisions that could influence the performance, which you can optimize perhaps by knowing a little bit about which transactions come in at runtime? All right, very good. So maybe we can already do some operations, something expensive like a join, for instance, already in advance. Or perhaps if we don't completely do it in advance, but we do preparation in order to make it very efficient. What kind of preparation could that be? Very good. Hashing data, for instance, okay. Yes. And in general, I mean, hashing is one valid way of distributing data across different nodes. So you can calculate a hash value in order to decide where to put one specific row of a table. And if you partition two tables using the same hash function and using a column from both tables that will be often joined together, then you ensure that a table partitions from different tables that join together are already located on the same machine, and therefore doing the corresponding joins becomes much cheaper. Okay, very good. I think we covered the primary points here. So if we know in advance which transactions come in, we can exploit that, for instance, in order to partition our data well, or generally to decide where to locate which data and how often to copy things and so on. And that can make processing at runtime much more efficient. So I covered the different points. I think we have essentially covered all of them. So because main memory has become cheap, we want to exploit that and actually store the database in main memory. Here, we have already heard that recovery can be difficult, but what we can do is that we simply create multiple nodes, independent machines, which store the same data. And if one of them crashes and loses the main memory content, we can just use data on the remaining nodes that have the same data and remain online. We're going to see in more detail how precisely we are going to do that. We have short-running transactions without disk stores, so why not just execute them serially? And we don't need any concurrency control like the ones that we have seen anymore, and it simplifies things a lot. And because we know a little bit about which transactions will come in at runtime, we can exploit that in order to do pre-processing, which makes runtime processing much more efficient. All right, so this is a little overview of the design decisions that HStore makes. Let me quickly move the chat. Here you see a high-level architecture outline of the HStore system. So here on the left-hand side, you see a couple of components that are invoked before runtime. On the right-hand side, you see components that are involved in runtime processing. So here, before runtime, you already assume that we have a lot of information given. We have, of course, the database schema. We have some information about the cluster on which we want to deploy our database. We have stored procedures, essentially meeting those transaction templates, and we have a sample workload given. And using that sample workload, we can, for instance, see which tables are often joined together. And then using this deployment framework, we try to optimize the whole setup. We try to decide the physical data layout, which means essentially deciding where to store which data on our cluster. We already compile the stored procedures, which also saves runtime overheads, and we can already make certain optimization decisions in query planning. Now, at runtime, we receive transactions as input. You see this acronym OLTP here, which stands for Online Transaction Processing. So this designates workloads that generally contain a lot of transactions. At runtime, we use those precompiled stored procedures in order to execute those transactions that correspond to the templates that we have seen before. And we might need to coordinate the execution with different nodes for transactions that touch data which is located on different nodes. Often we are lucky and can already find the data which is relevant for a transaction on one single node. We can increase the chances for that by choosing a good data partitioning at preprocessing time. And altogether, the system aims at providing asset guarantees while still being very highly available and having a very high transaction throughput. So in the following, we're going to see some of those design decisions and some of those system components in more detail, starting with preprocessing. And as we have already said, in preprocessing, we have given transaction templates and an example workload. We compile those transactions as stored procedures, and we optimize the data layout. And here are a couple of examples of what that could entail. For instance, if you have a table which is frequently accessed, and maybe the table is not even too large, then it makes sense to store one copy of that table at every node, which increases the chances that we have all required data for a transaction on the same node. And the other point is also something that somebody already brought up. We can store together joinable partitions of different tables on the same node. And if we know in advance which joins are frequent, then we can optimize the data layout in order to make them particularly low overhead. We have already discussed that HStore executes transactions serially, and here you have again the summary of why we want that. The previous motivation for interleaving steps of different transactions was that they sometimes run for a long time and sometimes they stall waiting for data from hard disk. And now we have very short running transactions and we have everything stored in main memory. So just serially executing the transactions actually works very well. Of course, that makes fault tolerance and recovery more difficult because if data is stored in main memory, it means that we lose all of it if there is a system crash. The way in which we become fault tolerant is by replicating data across different sites. Of course, here the tables are typically too large, so we cannot store an entire table on a single node. So instead of that, we partition the rows by their primary key value, for instance, across different nodes in a cluster. And then we can use schemes that guarantee a k-safety, which essentially means even if a k nodes in your system crash at the same time, then you will still be able to recover from that without losing any data. So this is about being smart about how you distribute those different copies of your table partitions across the nodes in the cluster in order to make sure that you don't lose any data as long as not too many nodes crash at the same time. After a node crashes and comes back online, it needs some kind of data source in order to obtain the data that it is now missing. In our case, since data is in main memory, all of the data will be erased by the crash. So now this node needs to get updated. In our previous in lectures, we have seen the Arius algorithm, and here the source for recovery is basically the persistent state on hard disk, and in particular, the log entries, specifically the so-called redo log entries, meaning those entries which enable us to redo updates to the data. Now, here, the source for recovery is not hard disk, but it is another node in the same cluster, which has not crashed, and therefore still has the data available in main memory. So in this case, we don't really need to produce any log entries for redoing things. And we certainly don't want to write any log entries to a hard disk, because we generally try to keep everything in main memory. So in this case, we don't need any log entries for redoing things. We still have to log a little bit in order to undo things, because in this system, still transactions could abort, and then we have to undo their effects. But again, those undo log entries, they don't have to be written to hard disk. They can remain in main memory. And also, we don't need to store them for a long time. We execute transactions serially, so we only have to store log entries for the currently executed transaction that we can discard after the current transaction has committed or has aborted and has been cleaned up. One little question: why is it again that we don't need to store those undo log entries to hard disk? Couldn't it happen that at the crash, we have some partially executed transactions whose effect we still need to undo? Yes, very good. So here we actually benefit from the crash in the sense that all the effects of partially executed transactions are automatically erased, same as everything else in their memory. Exactly. This is why we don't need to log any persistent undo entries. Very good. All right. So in some cases, we have to involve multiple sites into transaction execution. HStore tries to be smart about where it executes those transactions. In particular, we try to make transactions either one-side or one-shot transactions. One-side transaction is a transaction which can execute on one single node in the cluster, which makes things very efficient to execute. And this is something for which we can increase the chances during pre-processing by selecting an appropriate data partitioning. There's also one-shot transactions, which is transactions that involve multiple nodes. Perhaps the required data is not available on one single machine. And here we benefit, first of all, from executing transactions serially. The node which initiates a transaction simply assigns a transaction timestamp at the very beginning, and then we will execute those transactions in the order of the initially chosen timestamp. So if one node gets a set of transactions issued by other nodes, then it will execute those transactions in the order of their timestamps. One thing that is important in this context is that the different nodes need to have clocks that are pretty much synchronized with each other. So here the assumption is that we can guarantee that, so that the timestamps assigned by different nodes are consistent. Then we can execute the transactions in the order of those timestamps. And if it is a one-shot transaction, it means that is a relatively simple distributed transaction. So we essentially initially can determine which is the work that each of the participants has to do. And then we distribute those transaction parts to the different nodes, which will execute them in timestamp order. All right. So this is a high-level overview of the HStore system, and I shed light on a couple of key design decisions. This is one system that belongs to this class of so-called NewSQL systems and tries to combine high availability and performance with a strong formal guarantees. So here we don't have eventual consistency, but we have a complete consistency. And in order to get there, we have exploited a couple of properties of modern data processing workloads and of modern hardware. On the following, we're going to see another system that is typically counted among the NewSQL systems, which is by Google. It's the Google Spanner system. Now, this is a globally distributed database system. It is nowadays available as a product by Google, and it supports the SQL queries with ACID transactions. And in particular, one key point of that system that we will be discussing about in the following is that it offers external consistency at a global scale. And it is claimed that this is the first system to offer external consistency at a global scale. Now, external consistency is actually even stronger than serializability, which we typically expect from ACID transactions. It essentially means that if a transaction T1 commits before T2, then T1 is serialized before T2. So serialized means that everything looks as if transaction T1 had executed before a T2. The database looks like that, and everything that the customers view is consistent with that as well. So here the order of the commit timestamps is consistent with the order in which those transactions are serialized. Well, not necessarily. So that is actually, I will resolve that in a second, but I already wanted to ask this as a question precisely. What is the difference between this external consistency guarantee and the traditional ACID guarantees? Does anyone have an idea about how this guarantee differs from the traditional ACID guarantees? Anyone has an idea about what is different compared to the guarantees that we have seen so far? Very good. Yes, exactly. So for the traditional serializability that we have seen, there's no particular dependency on like the order in which transactions are serialized can be different from the order in which they have been submitted or committed, because the guarantee of ACID transactions is just that the system looks as if transactions had executed serially in some order, but it doesn't specify in which order their transactions have to execute. So this is kind of a stronger guarantee than what database management systems typically make. And one first difference to HStore, which we will see in the following in more detail, is, for instance, that here we try to guarantee this property at a global scale, meaning we have a distributed system that spans the entire globe, and it makes it very challenging to do things such as synchronizing the clocks of different nodes, for instance. So HStore doesn't necessarily have the same ambition to globally, to essentially make this work at the global scale. So the motivation for external consistency is, for instance, the following scenario. So we assume that we have a database which stores bank accounts, and we could have a scenario in which a client wires money to one account with a first transaction, and then later submits a second transaction which checks whether the money has already arrived on the new account. And so before we discuss about how we can achieve external consistency in the Google Spanner system, maybe first let's see what external consistency would mean in this scenario. Can anyone tell me why external consistency would be important in this simple scenario here? Yes, very good. So from the client perspective, the client would expect that after having wired the money, now when checking the account, then the money should actually show up. If that is not the case, then the client might get confused or think that the money has been lost and so on. So it wouldn't be great. So in those cases and in other cases, it would be great if the commit order from the client's perspective actually correspond to the order in which those transactions have been executed. All right. Now, one first approach that comes to mind in order to guarantee external consistency is the one that we see here. We could use something like a two-phase locking, for instance, and we could acquire the locks at the beginning of transaction execution. Then we pick some commit time, which happens somewhere while we are holding those locks, and in the end, we are releasing the locks for the transaction. And this seems to work well because as long as we're holding the locks, we are blocking other transactions from getting access to those objects, and therefore the commit timestamps should be consistent with the serialization order. Now, what is the problem with this approach in a distributed system? Okay, very good. Yes, the clocks on different nodes in the cluster might not be perfectly synchronized, especially if you assume that this cluster is distributed around the globe entirely. Exactly. So that is the starting point for an extension that they call the TrueTime API. It is based on the insight that you can never make sure that your nodes will be perfectly in sync all the time. Already, they use a specialized hardware in order to keep those clocks on different nodes very precise. They use atom clocks, basically. But despite of that, there's still some regular synchronization between nodes needed in order to bring those, in order to limit the deviation between different clocks. The longer you wait without synchronization, the more the uncertainty about the true time on one single node grows. And the TrueTime API essentially keeps track of how uncertain we currently are about the precise time. So here we have essentially an interval that somehow limits the current true time. We say it's somehow between 11:04 and 11:06, for instance. That is the interval, and you are pretty sure that the true time is somewhere within this interval. But the size of this interval grows over time if you don't have any synchronization. So here we essentially get from the true time API not one single time point, but rather a time interval. We have some earliest possible time and we have some latest possible time. And the true time is somewhere in between those two extremes. The interval of uncertainty, essentially the expected deviation between the best guess for the current time and between the latest and earliest possible time, that is written as epsilon in the following. And using this true time API, we can proceed as you see here. We essentially acquire logs on the objects that a transaction is interested in. And now as a commit timestamp, we use the latest currently possible time retrieved from the true time API. So basically we use a commit timestamp for which we are absolutely sure that it has not yet passed. And then we simply wait. We essentially wait out the uncertainty in time, which means that we have to wait for 2 times the epsilon, which is just the width of this interval of time uncertainty. And if we wait for this amount of time, then we are sure afterwards that our commit timestamp is now in the past. Because we have waited long enough, we can be sure that this point in time has already passed. And once we are sure of that, we can release the logs on all of our objects, because then we are absolutely sure that at the time of our commit timestamp, we actually did have the logs on all the relevant objects, and therefore no other transaction could have obtained the logs or obtained a commit timestamp which is inconsistent with that. Now, this is what it looks like here, illustrated graphically. So we have the time at which we acquire the logs, and then we use that plus epsilon as the commit time. Then we wait for 2 times epsilon, and finally we release our logs. So that is a key point of how they achieve external consistency in the Google Spanner system. And essentially, you see that they have to go to certain lengths in order to make sure that they account for the uncertainty about the precise point in time that you have when having your nodes in a globally distributed system. So for HStore, for instance, we have assumed that we can keep the clocks of the different nodes approximately in sync far enough. Here, we deal with this uncertainty in terms of time in a much more principled manner. So the Spanner system has a lot of interesting details to it, but we are not going to discuss about all of them. This is perhaps one of the most interesting features of the Spanner system. Here we essentially aim for even stricter guarantees than what ACID transactions usually provide. And that concludes our chapter on a NewSQL. So now we have seen traditional distributed database management systems, NoSQL systems, and NewSQL systems, which all provide different trade-offs between the consistency guarantees that they make and the kind of availability and performance goals that they strive for. So that is the end of the material. Is there any questions about this material for the moment? Okay, that is a good question. Why are modern transactions shorter? Well, modern transactions are executed completely automatically, first of all. Previously, that didn't necessarily have to be the case. There might have been some steps in there which required, for instance, input from users. And whenever you have that, it slows down transactions significantly. So yes, I think less human involvement, that is one big reason. Yeah, I think that perhaps like when picking one specific reason, then I would probably put that. Any other questions on this for the moment? One little announcement for the ones among you who are also taking the practicum. I wrote a message on Piazza. We already have the session, the practicum session today, now directly here after the lecture. We initially also had the questions about when the next lecture is. And the next week, we will have the semi-final study days. Afterwards, we will have the Thanksgiving break, so there won't be any lectures. So the next lecture that we will have is, I believe, the 30th of November. You can find the precise date in the academic calendar. And yes, it is the 30th of November. All right, good. Then in this case, I think we can conclude here. I wish you nice holidays and good luck for the semifinals, if you have any. We will see again on the 30th of November, or now directly in the next session in case you're taking the practicum. Have a nice weekend, and then we see again on the 30th.